Hey, my name is Mark Buehner, and my talk is entitled Towards Strongly Coupled Data Assimilation in Environment Canada. I'd like to acknowledge my co-authors, Sergey Skachko, Alain, Caya, and Alex Komarov. So here's an overview of my talk. So I'll start by giving an overview of the current numerical weather prediction systems and the role that SST and sea ice analyses play within these systems. And then I'll talk about why we want to consider going towards strongly coupled data assimilation. Then I'll talk a bit about the software known as MIDAS that we use for increasingly for many components of Earth system data assimilation at Environment Canada. And the basic idea behind that is that by first using the same software and also a simulation algorithm for each Earth system component, this will facilitate the gradual transition towards coupled assimilation. I'll talk briefly about one of the important roles that SST analysis plays within the current NWP assimilation system. Then I'll talk about some details about our Environment Canada sea ice analyses that we've developed that uses the MIDAS software. This includes ice concentration, but also ice type and ice thickness analyses that are being developed. And then I'll talk about the new SST analysis system that we implemented within MIDAS and how that serves as an important first step towards a full 3D ocean assimilation using the LETKF, or Local Ensemble Transform Kalman filter algorithm that is also within MIDAS. And finally, I'll talk about some of the next steps and small incremental steps moving towards strongly coupled assimilation. Okay, so this figure shows the main numerical weather prediction systems that are operational in Environment Canada. So we have both deterministic global system, ensemble global system, and a high resolution, so limited area deterministic system, and also a regional ensemble prediction system. So the global medium range deterministic and ensemble NWP forecasts produced by these systems are using coupled ocean ice model, but they're initialized still using fully uncoupled data assimilation systems in the operational system. So the global ensemble system, known as GEPS, standing for Global Ensemble Prediction System, provides the ensemble covariances for all the other systems, because we use four-dimensional ensemble variational assimilation algorithm for the deterministic systems and also as a component of the ensemble prediction system. And this assimilation algorithm relies on ensemble covariances produced by the global ensemble prediction system. We've developed in-house global SST and both global and regional sea ice analysis systems that provide their analyses to all the other systems. And that's shown on this slide how that happens. So we have along the top row the SST analysis system, daily analysis system, and then on the next row the sea ice analysis system, which operates every 6 hours, just like the atmospheric data assimilation systems, which is shown here on the third row. And then finally we have an ocean assimilation system, which operates daily. And so we can see how both the atmospheric and the ocean assimilation systems feed into initializing the coupled medium range forecasts, and how the SST analysis and also the sea ice analysis feeds into many of the other systems. And a lot of those connections are detailed here on this slide. So, so indeed, all those arrows you saw on the previous slide indicates there are many connections between these uncoupled assimilation systems. The SST analysis is used in many ways. So for sea ice observation quality control to remove spurious non-zero ice concentrations retrievals, also to remove sea ice in a simple persistence model we use for cycling the sea ice within the sea ice analysis system. And as a lower boundary condition for the background atmospheric forecast in the NWP system. And it's also the SST analysis is assimilated as if it's observations within the 3D ocean assimilation system. The sea ice analysis is also used in many ways. It's used for deciding where we assimilate either satellite SST observations or artificial observations that are set to the freezing point under sea ice. And it's also used as a lower boundary condition over lakes for the atmospheric forecasts in the NWP systems. And it's used to partially specify the ice concentration for the ocean ice, initializing the ocean ice model forecasts. Finally, the ocean ice state from the ocean ice prediction system is used for the lower boundary condition of the sea ice, of both sea ice concentration, thickness, and also snow depth over sea ice, over the ocean, for the forecasts within the NWP systems. So there's many connections, there's many, in a sense, couplings between these uncoupled assimilation systems. So if we wanted to think about moving towards a fully coupled data assimilation system, there are several potential advantages. The first is it reduces the number of systems that need to be run and maintained. And it also makes it, I think, easier to include all the inherent links that we want to include between the components. The observations of one component can provide corrections to another component through the coupled ensemble covariances, both within the LETKF and the 4D ENVAR assimilation algorithms. And this can help to ensure some level of consistency near the component interfaces of the different Earth system components. The observations directly related to multiple components, Earth system components, can be more optimally utilized. An example of this that I'll show later is surface-sensitive radiances. This figure shows how at a high level using fully coupled data assimilation simplifies things, because we have a single system using the fully coupled forecast model, a fully coupled, strongly coupled data assimilation component, and all cycling within a single system, all components. So there are to initialize the medium range coupled forecasts. So there are, of course, a couple of disadvantages as well. This represents a big change from the figure that I showed previously. So implementing, and of course, when we work with operational system prediction systems, it's usually much easier to implement a series of small incremental changes rather than this very large change to the system. It also introduces certain reduction in the amount of flexibility in the systems, since all the components must share the same common data assimilation time window, the same observation cutoff time, and they have to run on the same time slot on the computer. And for the assimilation component to be strongly coupled, they need to use the same assimilation software. So talking about the assimilation software, at Environment Canada, we've developed what we call MIDAS, which stands for the Modular and Integrated Data Assimilation System. It's a unified data assimilation software framework that's used both for research and operational use at Environment Canada. And it has two main objectives. The first is to avoid the redundant work within the organization, so we can share code and work together on a common shared code framework. And the second is to facilitate this transition towards coupled data assimilation, where we strongly couple the data assimilation of different Earth system components. The code is modular, and it generalizes the implementation of many of the data assimilation elements, here represented by their matrices and vectors, the observation operator, observation error covariances, background error covariances, and state vector and observation vectors. This enables the use of data assimilation algorithms for various applications. So for instance, atmosphere, sea ice, ocean, using mostly the same code. MIDAS currently includes this following list of functionality. So variational data assimilation algorithms. This is used for operational NWP, the LETKF algorithm and various flavors of it. Also related ensemble inflation and ensemble recentering procedures. These are all used for operational NWP as well. Bias correction, quality control, and thinning algorithms for all of the numerical weather prediction observation types. The assimilation of atmospheric constituents, including ozone, is included in MIDAS. Also, observation impact estimation, which we recently made operational both a hybrid FSOI and ensemble FSOI approaches. And so finally, most relevant for this workshop is the fact that CICE and SST analyses, both using 2D VAR, are implemented within MIDAS. And having this implemented and tested so far with 2D variational approach makes it relatively straightforward to also test ensemble and more advanced variational assimilation algorithms for these applications. And also we've started implementing a limited amount of 3D ocean assimilation capabilities using the LETKF within MIDAS. So MIDAS is made up of a series of about 20 different Fortran programs that implement all of the data assimilation related functionality. And these programs all use a shared set of about 100 Fortran modules. So we see on the left here some examples of different Fortran programs in MIDAS. So for instance, the LETKF, the variational data assimilation, OB selection for pre-processing observations, ENS post-process for manipulating ensembles, etc. And all these programs rely on different Fortran modules that some of them are relatively high level, like minimization, which is used for a lot of the functionality for variational data assimilation, ENKF module used for all the ensemble data assimilation computations. But then we have lower level modules, for instance, OBSpace data that contains all the observation related data and also functionality. And this similarly for grid state data related to storing gridded fields of data and also related low-level functionality. So now I'll talk a bit about the role of SST in current NWP systems, assimilation systems. So the NWP system already needs SST or surface skin temperature over the oceans. This is because we assimilate surface-sensitive microwave and infrared satellite radiance observations that are an important set of atmospheric observations observing the lower troposphere over the ocean. But these observations are also sensitive to the surface skin temperature. So currently we use the SST analysis for assimilating these as inputs to assimilating these observations, but the SST analysis may not be accurate enough to provide an optimal atmospheric temperature and humidity corrections. So in other words, errors in the skin temperature causes errors in the air temperature, which we're mostly concerned about for the NWP data assimilation. So instead, we use the SST analysis as a background state for the skin temperature, and we compute analysis increments along with the air temperature increments within both the 4D ENVAR and the LETKF algorithms. But then these increments to the skin temperature are not used for the forecast. This is similar to the approach described by Froloff in a 2020 paper. So it's important to distinguish different types of SST in this context. So the daily SST analysis that we produce at our center typically aims to provide what's called a foundation SST, which is unaffected by the diurnal cycle, whereas the surface-sensitive radiance observations, they're really more closely related to the surface skin or the subsurface subskin temperature, very close to the surface. So in a paper by Akela in 2017, he used a model to relate the skin temperature to the foundation temperature for assimilating this type of surface-sensitive radiances and showed that it can provide an improved fit to the observations. And this is a figure on the right taken from the GHRSST website, just demonstrating how the skin and the surface skin, subskin temperatures can vary quite a bit from the foundation SST. So an example of the skin temperature increments computed in our operational atmospheric data assimilation system is given on this slide. So our global ensemble prediction system, it has very little ensemble spread for the ocean skin temperature. This is because all the members use the same SST analysis. So every member is initialized with the same SST field. And the spread can only develop from for the ocean surface layer, from the ocean surface layer parameterization within our atmospheric model. So there's really no foundation SST uncertainty included in the ensemble spread. This low ensemble spread results in an unrealistically small skin temperature increments when assimilating surface-sensitive radiances in both the 4D, ENVAR, and LATKF. And these increments are very different. I'm not showing it here, but I've compared the increments of the T-skin from the NWP system with the daily SST increments from the SST analysis system, and they're really quite different from each other. We think that a coupled ocean-atmosphere covariances would provide more realistic SST spread, and it should allow for a better T-skin or SST analysis to be obtained within the NWP data assimilation system, and possibly allow for the improved or expanded use of surface-sensitive radiances within the NWP system, leading to improved lower tropospheric air temperature analyses. So now I have a few slides describing some details about our sea ice analysis system that we've developed. So we have an operational ice concentration analysis that's produced every 6 hours on both regional and global grids. It's used, as you've seen in previous slides, both for NWP and ocean prediction systems based on 2D VAR. And here the horizontal background error correlations are modeled using diffusion operator. We also produce analysis error estimate using a simple optimal interpolation approach to produce a measure of uncertainty to go along with the ice concentration analysis. And we've recently migrated all of this into the MIDAS software, making use of many of the existing MIDAS Fortran modules. And we're also in the process of developing ice type and ice thickness analysis systems. And the figure on the right here shows a verification score from a regional ice ocean prediction system versus IMS analyses of 48-hour forecasts, showing the proportion correct for the ice concentration averaged over the winter 2019-2020. And essentially, we see the values are very close to 1 over most of the Arctic and in Hudson Bay, and it's really along the ice edge where we have some reduced values of proportion correct total, but still not going below 80%. So this slide summarizes very briefly the different types of observations that are assimilated within our sea ice assimilation system. So our system assimilates many different observation types with a very wide range of spatial resolution. This includes SSMIS, ASCAT, AMSR2, ice charts from the Canadian Ice Service, and now recently SAR, synthetic aperture radar observations from the RadarSat Constellation mission, or RCM. For low resolution observations, the observation operator aggregates the ice concentration from all the grid points that fall within the observation footprint. And this is done to avoid constraining the unresolved smaller scales. So for instance, for SSMIS and ASCAT, the footprint sizes represented by these circles are much, much larger than the grid cell sizes of the analysis shown here for the regional at 5 kilometers, the global analysis at 10 kilometers. And so we want to be able to assimilate these observations, but only use them to correct the large scale component of the analysis and allow the higher resolution observations such as AMSR2, ice charts, and especially RCM to determine the smaller scale component of the analyses. This now is briefly describe our use of the RCM, synthetic aperture radar observations. So SAR, some of you may know, SAR data provides very high resolution and all-weather ice information, but still there are many image ambiguities which pose a serious challenge for fully automated use of these observations. But we've developed methods to do an automatic retrieval of ice information from SAR that, when assimilated with existing observation types, improves, especially where the high spatial resolution is important. And that's, for instance, near land and for smaller lakes, and where the CIS ice charts are not available. So on the left here, we have a SAR image and the resulting retrieval from our algorithm that's estimating ice concentration, and the areas in black show areas where the retrieval algorithm did not have sufficient confidence to be able to return a retrieved value. And on the right here, we're comparing the retrieved ice concentration value from SAR, comparing it with image analysis ice concentrations over a full year of data, including approximately 4,000 RCM images. If we can see a very good agreement across all the different ranges of ice concentration value. This slide shows some of more detailed information. I won't go into the detailed information, but essentially just to say that the ice concentration retrieval is based on a simpler ice, no ice retrieval algorithm that we apply at a much smaller scale, and then aggregate the results of that ice or open water retrieval to come up with the ice concentration, final ice concentration retrieval. And there are many references on this slide to give more information. And this slide shows the impact where we have improvements from simply adding the RCM data to the existing system that assimilates all the other types of observations that I outlined. And we can see very large improvements, especially over the small lakes over Canada and also near the coastline in the ocean areas. We're also developing an ice type retrieval algorithm using RCM data as well. And the idea here is it's based on computing empirical probabilities for the two ice types, first year and multi-year ice. The technique is applicable under cold conditions only for HH and HV satellite images, SAR images. And the probabilities are computed for two predictors, the HV-HH polarization ratio and the spatial standard deviation of the HV signal. The overall accuracy of the multi-year and first-year ice from the RCM evaluated against Canadian Ice Service image analyses is as high as 96 or 99.7%, depending on the ice type. And the figure on the right gives an idea of the probability of multi-year ice occurring for all different combinations of these two predictors, so the polarization ratio and the spatial standard deviation of HV. This slide shows an example of this ice type retrieval. On the left, we see the original SAR image, and in the middle, the retrieval from RCM, showing where in yellow, where we have first-year ice, and in red, where multi-year ice is detected. And on the right, we have corresponding to the same time and location, the Canadian Ice Service image analysis indicating the partial concentration of multi-year ice, where the darker colors correspond to more multi-year ice. So we can see a very good correspondence. This is another comparison against a CIS regional chart where we simply added RCM. We combined the RCM ice type analysis with an existing ice type analysis system that's based on passive microwave and scatterometer data only, so quite low resolution satellite observations. And we can see that adding the RCM data has impacts mostly in the areas where you'd expect higher resolution to be beneficial. So in narrow channels, for instance, this location where we have a better agreement when using RCM down here, and also in this area. We're also working on developing an ice thickness analysis where we use 2D VAR approach to assimilate ice thickness retrievals both from L-band passive microwave observations from SMOS, and that's mostly for the thin ice, and also for thicker ice from the altimeter data from Cryosat-2 instrument to produce a single combined ice thickness analysis. Comparisons with the unconstrained thickness within the current ice ocean prediction system shows many differences. The current system doesn't assimilate any ice thickness information. And when we evaluate both using the ice bridge observations, it shows that the thickness analysis from satellite data could lead to some pretty large changes and improvements for the model ice thickness, mostly for ice within this intermediate range from about 2 to 3.5 meters thickness. So in these figures here on the left, we have the ice thickness analysis for a particular day, and on the right, for the same day, the thickness from a regional ice ocean prediction system. And we can see these large areas within the Arctic where the prediction system has much thinner ice, and this is specifically in the range where we think the analysis is much more closer to reality, closer to ice bridge observations. Now I'll talk a bit about SST and ocean coupled assimilation. So firstly, there'll be a lot more detail on this topic from Sergey's talk that's coming up in this session. And so he's developed a new MIDAS-based SST analysis system, whereas the operational system is based on optimal interpolation, which is difficult to modify and maintain. The new MIDAS-based system relies on the modern code used by many other data assimilation systems at Environment Canada, and it uses a 2D variational assimilation with a diffusion operator, B matrix similar to the sea ice analysis system, and much of the code is shared with other applications. And assimilating the SST observations in MIDAS certainly facilitates work towards full 3D ocean assimilation using MIDAS, for instance, the LETKF algorithm, and that in itself is a incremental step towards fully coupled data assimilation. So, as I mentioned, so after this ability to do SST analysis within MIDAS, it was fairly straightforward to implement an ensemble Kalman filter, a local ensemble transform Kalman filter, the LETKF within MIDAS. And we chose the LETKF instead of the ensemble variational approach to start with, since spatial localization within the LETKF is much simpler. It only requires the ability to compute distances between observations and grid points, which is quite straightforward, even for the ORCA grid used by the ocean model. And horizontal localization, whereas horizontal localization is implemented in the ENVAR using spectral transforms on a Gaussian global grid. So that would require lots of interpolation back and forth between grids, which could be problematic near coastlines. So initial tests using ensembles from an existing 20-member coupled forecast and recentered on a deterministic state shows a way of using LETKF not only to do ensemble data assimilation, but to produce a deterministic analysis. And now Sergey is preparing a full suite system to enable cycling of the LETKF with an ensemble of NEMO CICE forecasts forced by our atmospheric ensemble system. So here's a simple example, a single example where we assimilate only in situ SST observations, either using the LETKF with 20-member ocean ensemble, or using the 2D VAR, as in for the standalone SST analysis system. And we can see that we get fairly similar SST increments. And more interestingly, looking at a vertical zonal cross-section at this line, for the temperature increments in the LETKF, we can see very realistic looking increments through the mixed layer and then changing sign just below the mixed layer. And this seems to be consistent with a shallowing of the mixed layer depth in this area near Newfoundland. So we think we can build on this early work of developing an ocean LETKF, potentially by introducing an intermediate step towards fully strongly coupled data assimilation, using an approach similar to the interface solver introduced by Frolov in 2016 study. So by using the ensemble of atmospheric model integrations, or the ensemble of atmospheric model integrations can use the SST ensemble from the ocean system, valid at the initial time, and then held constant through the short-term forecast period. Then the ensemble of ocean model integrations would be forced by the atmospheric members. So essentially, we'd have two-way coupling in an indirect way between the ocean ensemble and the atmospheric ensemble. And then the same SST and sea ice and principal sea ice observations would then be assimilated both in the NWP system and the ocean assimilation system. And this would remove the need for a separate SST and sea ice analysis systems. The benefits of this approach I think it would maintain a much more realistic, would allow us to maintain a more realistic SST and skin temperature ensemble spread within the NWP assimilation cycle. And that should lead to improved use of existing surface-sensitive atmospheric observations. But it's also more flexible than moving directly to a fully coupled data assimilation cycle, since both the model and the data assimilation procedures are still separate, even though they're interacting with each other. After establishing a MIDAS-based ocean LETKF, I think this small incremental change should bring some, but not all, of the coupled data assimilation benefits to the NWP system. So I think it's an interesting approach to look at. And sort of the flow chart of how this would work looks like this, where the atmospheric ensemble is forcing the integration of an ensemble of ocean ice integrations, and then the resulting background state, the ensemble of SST fields and sea ice, would then complement the background ensemble of the atmospheres to allow coupled assimilation within the atmospheric assimilation system. We're essentially coupling the atmosphere with just the SST and the sea ice fields. And this would cycle this way indefinitely. So my last slide, just to summarize and talk a bit about future research. So we think increasing the use of MIDAS at Environment Canada for both ocean and sea ice will improve the efficiency both of developing and maintaining data simulations for either Earth system component, because we'll be working with shared code. So there's a team of software developers and scientists working on this code that can work together, while also making future research moving towards strongly coupled assimilation possible. The sea ice and SST analysis systems already use MIDAS, and the next step that we're already working on is to work towards full 3D ocean analysis, ensemble ocean analysis system. And finally, I think the interface solver approach from Frolov is a interesting looking incremental step to move towards fully coupled assimilation, but the interface observations, so here the sea ice and SST observations need to be assimilated in both systems, but that's quite straightforward if both systems are using the same software, the MIDAS LETKF. Okay, thank you. That's all I have.